Everybody's here, so let's start with our second session with Bernhard Hanke from Universität Augsburg in Germany again. So he's kind of a coarse personality, are you? Let's go.
Coarse and rough. So you take the microphone, then I take this one? Yes. Okay, so it seems that this is working. It's another talk about positive curvature geometry, but in some sense I'm on the other extreme. We are talking about scalar curvature, which is of course a much weaker curvature notion than sectional curvature. And so we heard in the previous talk that there are very few examples of positively curved manifolds in the sense of sectional curvature. But when we look at scalar curvature, the picture is different. And so we have this, I would say, guiding conjecture, which is still kind of one of the leading principles of the fields of positive scalar curvature geometry and topology. And I stated it in a slightly vague way, namely, I say that a closed connected manifold of dimension at least 5, that is always important here, admits a positive scalar curvature metric if and only if a generalized index invariant on M vanishes. So it is imprecise in the sense that it includes both the spin and non-spin cases. So in the spin case, this index invariant is the A-hat genus, or then more generally, this is the contribution of Rosenberg, an index living in some K-theory connected to C-star algebra of the fundamental group of M. And in the non-spin case, this, say, quote-unquote generalized index invariant is supposed to vanish. So what I want to say here is that we have one simple criterion conjecturally that allows us to decide if a given manifold admits a positive scalar curvature metric or not. And there are different strands. In the recent years, as we can say, especially this index invariant itself, and it's not non-vanishing, has been explored a lot in very general contexts, C-star algebras, coarse geometry, whatever. And this is always to decide whether a manifold does not admit a metric of positive scalar curvature. And this conjecture, of course, makes a prediction when it, not only when it does not, but also when it does. And so in this talk, I would like to explore more that direction. So let's see some results in that direction that we have. So this is maybe the most impressive contribution to that conjecture, namely, we know that it is true in the simply connected case. So this is the famous paper of Gromov and Lawson from 1980, where they introduced their surgery technique and the connection to Bordism theory, and then later on by Stefan Stolz in the spin case, using connections to more elaborate methods in topology. Especially the atom spectral sequence came into play here. And so the most difficult part here, or kind of non-trivial part, is to construct these metrics of positive scalar curvature. So there must be some very general construction principles, contrary to the case of positive sectional curvature. And these construction principles actually allow us to connect the problem into topological setting and a topological language that can then be treated by fairly abstract and efficient methods from algebraic topology. So in that sense, maybe this talk is the most algebraic topological one, in the sense that the geometry is really treated within the language of topological objects. I will tell you later what this means. But let us look a little more than at a little more examples. So the non-spin case means, so the prediction is that if the universal covering of M is a non-spin manifold, then M is conjectured to admit a positive scalar curvature metric, so no obstruction at all. But here we have an interesting, a very interesting finding of Thomas Schick, namely the conjecture is actually wrong. And this, I mean, somehow people tend to put this aside a little bit and still look at this conjecture, but I mean, it is just wrong in general. And this is a not very good sign, I would say. At least for infinite fundamental groups, it's definitely wrong. The point is that the index obstructions in the non-simply connected case do not cover the whole of all obstructions against positive scalar curvature. So there is also the minimal hypersurface obstruction, which is in some sense complementary to the index theoretic one, and which especially also works in the non-spin case. Okay, so and then we have a stable version, which is, I would say, for geometers not very interesting, because this tells us that not M itself admits a positive scalar curvature metric under some circumstances, but after multiplying it with a number of Bott manifolds, B8. And I would say this is not what we are interested in. I mean, we want to know whether M admits a positive scalar curvature metric or not, but the stable conjecture is really connected to this more abstract index theory, and then we can treat that statement. And so another point is that for finite fundamental groups, we do not have counterexamples to the conjecture. Let us now really look at the non-simply connected case. And in this talk, I would like to concentrate on finite fundamental groups of odd order. So in general, in the odd order case, the previous conjecture can be written down in this more simple way. This was done in a paper by Jonathan Rosenberg. Namely, if we have a finite fundamental group of odd order, then the conjecture says that M admits a positive scalar curvature metric if and only if the universal cover does. And so we can phrase that also as a symmetry problem, namely, okay, you have a manifold M tilde, and you have a finite group of odd order acting freely, and then the statement is that then M tilde admits a positive scalar curvature metric if and only if it also admits one which is invariant under the action. Okay, so that is this statement here. And one remarkable fact is that we do not know this conjecture in many cases. So once we look at non-simply connected manifolds, the world of positive scalar curvature manifolds is pretty much non-understood, I would say. Contrary to, I think most people believe, we cannot say much. So one particular case was dealt with in this paper by Rosenberg. So where is the pointer? It is backside, okay. So this is the case basically of cyclic fundamental groups. And more generally, by using transfer arguments, one can then pass to fundamental groups with the property that all P pseudo subgroups are cyclic for every prime P. Here we are restricting to odd primes, of course. So these are the fundamental groups with periodic cohomology. And then there is another remarkable and important case, namely that of elementary abelian P groups, or alternatively groups all of whose P pseudo subgroups are elementary abelian. So we need an additional assumption, P aterality, which I will consider, which I will define in a second. And this case was treated in a paper by Boris Botvinnik and Jonathan Rosenberg in 2001. And actually in there, so there is a homological computation which had a serious gap, I would say. So I then took up the topic and wrote a paper on that case, which was published in 2016 in the Journal of Topology. So already that case is really non-trivial. But apart from these two cases, as far as I know, for odd order fundamental groups, finite fundamental groups, there are no cases where we really know what's going on with respect to the Komov-Lawson-Rosenberg conjecture. So we do not know whether positive scalar curvature metrics exist or not. So what does P atoral mean? This is an assumption which I have to make, or we have to make in this theorem. And this is some kind of finite analog of torality, which would mean that you have cohomology classes, rational cohomology classes in degree 1, such that the cup product of these classes evaluates non-trivially on the fundamental class of the manifold. So this is the same thing just with Z mod P or P to the K coefficients. I say that a manifold as M is P atoral if whenever I take D classes in cohomological degree 1, I take the cup product evaluated on M, then I get 0. So if that happens, if we do not get 0, then I do not know if we have positive scalar curvature or not. So under this assumption that this does not happen, we have this existence result here. And so just a short remark. This is always the case if the fundamental group of M has smaller rank than the dimension of M. So in high dimensions, this is not a restriction. So as I said before, this is a certain analog of torality. So if you take Z coefficients here instead of finite coefficients, then this means that you find one-dimensional rational classes such their cup product evaluates non-zero on M. So these are zero toral manifolds, as we might call them. And they actually do not admit metrics of positive scalar curvature, because then we have an index obstruction in the spin case. And in the non-spin case, we have the minimal hypersurface technique. We can namely take, so we work by induction. Let's take the final cohomology class CD. This is represented by a map from M to S1 to the 1 sphere. And then we can take a regular pre-image, which is a hypersurface of codimension 1, and we take a volume minimal representative in the same homology class, and then one can show that this also admits positive scalar curvature. So then we can go on by induction and arrive at a contradiction in low dimension 2, because the 2 torus does not admit a positive scalar curvature metric. So here I am, of course, skipping the regularity issues that are not a problem in dimension less than 8 or less than or equal than 8 in high dimensions. I do not want to enter this discussion now, but in principle, we have this the statement here that zero toral manifolds actually do not admit positive scalar curvature metrics. So this is just a remark which is not directly connected to the theme of my talk. But what is maybe interesting is that we can, of course, construct p-toral manifolds very easily by just taking a torus, D torus, which has fundamental group Z mod D, Z to the D, and then we can kill P times the generators in the fundamental group by surgery. So in this case, we get p-toral manifolds, and this is actually an open problem for your session. Do these manifolds admit positive scalar curvature or not? And actually, there is also a point which I find fascinating, and maybe I should talk to some of the experts here in the room. Is there any chance to mimic that proof, minimal hypersurface proof, in the case of finite coefficients? So, in fact, if you have a p-toral manifold for non-zero p, then we do not get these hypersurfaces anymore as smooth manifolds or anything, but we have to pass to more general objects, namely we have to use manifolds, say, with Z mod p coefficients. So slightly more general, and then maybe it is possible to mimic that proof, the minimal hypersurface proof, in that under these circumstances, but I do not know at all if that is possible or not. So here's an interesting open problem. But I would like to show you a path how we can prove the existence of positive scalar curvature metrics if the fundamental group of M is abelian, that's important, and of odd order. And of course R-toral for all odd P. So again, I'm restricting to odd order fundamental groups. I take the abelian case. And now if you look at one prime at a time, this basically amounts to passing from elementary abelian P groups to more general abelian P groups, which are of the form Z mod P to the K1 cross ... Z modulo P to the KR. So this is the generalization I would like to present here and what methods we use to construct these metrics of positive scalar curvature using topological methods. So this is the main theorem. And let me recall one important construction principle that has been very influential and very efficient and which is also basic for the existence results of Gromov-Lawson and Stolz. Namely, this is the connection to Bordism theory. So for an arbitrary topological space, X, let me recall what I mean by that thing. So this is a group, and the elements in that group are given by maps from some n manifold, a smooth closed n manifold, a D manifold n to X. So this is, so these are maps to X, and we divide out the Bordism relation. So this is the simple picture. We have a manifold N1, we have a map to X, another manifold N2, a map to X, and these are identified in that group if we find a manifold co-bounding these two, the disjoint union of N1 and N2. And of course there are many flavors of Bordism theory, oriented, spin, and many others. Let's not put so much effort to in this distinction, but this definition is really important here. So what does it have to do with positive scalar curvature? The point is that we can define a certain subgroup, which I call the positive Bordism group, and this just means that I restrict to representatives, to classes, which can be represented by maps from a positive scalar curvature manifold into X. Okay? So this is a certain subgroup. It's an abstract definition. We can write it down and then hope that something useful comes out of it. But you should really remark here, or it's important to see that we combine this topological definition directly with the geometric condition. So we put the geometric condition, a scalar curvature assumption directly onto the representatives of this homology theory or this Bordism theory. This is a very important principle here. Okay, so we have positive Bordism. And I call this a construction machine for positive scalar curvature metrics because we have the Bordism principle of constructing positive scalar curvature metrics. And the point is here we have to restrict to dimension at least 5. We look at the classifying map of the universal cover of M. So B pi 1 of M is the classifying space for the fundamental group. It's a topological space whose only homotopy groups are in degree 1, and it's equal to pi 1 of M. So we can actually think of that space as being constructed from M by adding cells, killing all homotopy groups from degree 2 onwards. Okay, so we take this special map, and this thing here, of course, represents an element in the Bordism of this space. And then we actually have the two following statements which are equivalent. M itself admits a positive scalar curvature metric, and the other is that this class represented by this particular map lies in the positive part of the Bordism of B pi 1 of M. So the picture is here that we have, it's the same one as before, but we have to find a picture like this where we have a positive scalar curvature metric on the left-hand map, and on the right-hand side we take the classifying map, and we have to be able to fill that thing. This means that we are actually in the positive part. And just to complete the statement is, I have to remark that in the spin case we work with spin Bordism. If M is a spin manifold, if the universal cover of M is not spin, we take oriented Bordism. So I do not want to say too much about the proof of this statement, because I think it has been explained in many talks, many places in the literature. The basic principle is that we have a surgery invariance statement. So if you have a manifold, you apply surgery to it to get another manifold of codimension at least 3. Then we can conclude that this new manifold also has positive scalar curvature. And actually, there is a more general principle than that. We can apply this to more general curvature properties, as was pointed out in a PhD thesis of Stefan Hölzel, a previous former student of Burkhard Wilking. But here in the positive scalar curvature geometry, I think this is the prototypical example. And once you have such a statement, a surgery invariance statement, then we have the connection to differential topology via Morse theory and the H-cobordism theorem, and then we are in business. And this is why such a statement has a chance to be true. Okay, so what can we do with it? I would like to go back to the computation in the case of elementary abelian P groups. I told you that in this case, for R-toral manifolds, we have a statement, we have an existence statement, and this amounts to computing the Bordism groups of the corresponding space B pi 1 of M, right? So this means we have to compute the Bordism group of classifying spaces of elementary abelian P groups. And this computation is exactly the one that was not finished correctly in the paper by Winnig Rosenberg, and I wrote it down in my paper. The statement is the following. We find very special representatives, namely, so look at these length spaces, L, 2m plus 1 in each odd dimension. We just divide out the free Z mod P action on an odd dimensional sphere. We can take a standard action, so a standard length space. And then we have canonical maps. You can take just a product of such length spaces and map it to a product of classifying spaces for the group Z mod P. Each of these length spaces has such a map to B Z mod P. You just take the product of these maps. And this is not enough to generate the Bordism. We pass from the classifying space of Z P mod K to the one of Z mod P to the R, which is the group that is appearing here, just by applying some group homomorphism. In some sense, you could think of that as a twisted product of length spaces, or I call it a generalized product of length spaces. And by the way, such a statement also has a non-trivial conclusion in the topology of group actions. So this is kind of going back to the classical work of Connor and Floyd in the 60s, where actually these groups were calculated to some extent, but this result here was not stated at this time. So here we need a new argument. And now let's see what classes here are positive, right? So which ones can be represented by positive scalar curvature manifolds? And we see that this is the case once at least one of these length spaces has dimension larger than 1. Because then you divide out a free Z mod P action on a 3-sphere or 5-sphere, you have positive scalar curvature, no problem. The only point that is left is you take a product of one-dimensional length spaces, which are S1s. So you have a torus here mapping to B Z mod P to the R, and then we cannot say if the corresponding class here is positive or not. So that's the point why we have to exclude these classes. But this is actually more or less the end of the story, because for more general groups, the computation of these Bordism groups is extremely complicated, or I would even say impossible. So this is the, I think, so for elementary abelian P groups, we have some result like this, but for more general abelian P groups, I do not have anything like that. And without such a computation, there is no chance to apply the Bordism principle to positive scalar curvature geometry, because, I mean, if we do not know this group, then let alone we cannot prove anything which classes are positive or not. Okay, so this is really a barrier. And so this is why I would like to simplify the setting in such a way that we can really apply homological computations. So not Bordism theoretic computations, but I would prefer to use homology of these classifying spaces, because then we have more methods of computation. And for sure we can compute the homology, usual homology of classifying spaces of groups much more easily than Bordism theory. But this means the following, and this is a key point of my talk. So in Bordism theory, we have maps from manifolds to spaces, and so we immediately know what it means that this manifold has positive scalar curvature. If we use homology, then we have more general sorts of representatives, no longer manifolds, but, for example, you can take singular cycles or simplices, and then you have to describe what it means that these objects have positive scalar curvature. Okay, so there is one very convenient setting to carry out such an argument, and this is within the world of manifolds with Bars-Sullivan singularities. And the point is that these are sufficient for describing homology, at least at odd primes. So this is the path that I would like to enter now, and we are talking about positive scalar curvature on manifolds with Bars-Sullivan singularities. So what is it? We fix some singularity types, as we call it. So this is just a sequence of closed smooth manifolds, and so the intuitive way of thinking is that these manifolds, or rather cones over these manifolds, are allowed objects within that category. So we allow certain singularities, which you might think of cones over these special singularity types, and so then we are no longer in the smooth world, but we have certain types of singularities, but well-controlled ones. The point is here that we have to iterate the process to some extent, and this adds a certain kind of combinatorial bookkeeping to the whole picture, and I try to describe it as easily as I can on this slide. I will give you a simple picture on the next slide. So actually we need a whole bunch of manifolds with corners. So manifolds with corners are always modeled on, locally modeled on corner models like this, 0, 1 to the k. So we have a corner point of codimension k, a dimension k cross u, and u is an open subset of some space n minus k, right? So this is then an n-dimensional manifold with corners. Maybe we take d minus k. Local models like this. And so we have certain decompositions of boundaries, namely the boundary decomposes into codimension 1 faces, where on each codimension 1 face we have an identification with a pi with such singularity type times a new manifold within that list. So this I means that we just take omega union I. Right, so this is an iterative process. We have a manifold A, empty set with boundary of that kind. Each boundary type has this product representation, and then we have smaller pieces that again have these decompositions. And then we have certain compatibility conditions for these different ways we can take boundaries. And maybe the easiest thing is to look at this picture here. So this is a manifold with a simple corner. And so here we have the interior part, which I call a empty set. And then we have the ith boundary part, which is the codimension 1 phase of this thing here. And I have to identify this with another manifold AI cross PI. AI is, you might think of this as this line here, and then we cross it with a closed manifold PI. Here we have the same thing with PJ, and in the intersection of these, we have then a new representation, AIJ cross PI cross PJ. And this goes on and on into bigger and bigger codimension. This is the picture of manifolds with Bars-Sullivan singularities. So we have a very well-controlled singularity types. And now I would like to introduce a notion of positive scalar curvature on those things. So for this, I assume that these singularity types are equipped with positive scalar curvature metrics. We can do that later on without any harm. So there is no loss of generality for what I have in mind. Let's assume that. We have positive scalar curvature matrix HI. And now I would like to say what it means that we have positive scale, that I have a distinguished metric on such a P-manifold A. So by a distinguished metric, I mean I have a general notion of Riemannian metrics, but along the singularity parts, which is this and this black line, I want a well-controlled behavior of these metrics, taking into account that on Pi and Pj I already have positive scalar curvature metrics. So this is then formally given by a family of metrics on these manifolds A omega, like a empty set, for example, or AI and AJ. And now the point is that when I restrict this metric to the boundary, then it has to be a product metric, namely the product of HI here, and then I have the metric G omega I on these, the given metric on this piece here, and the same thing here. This is a reasonable compatibility condition. And the second condition is that these products that appear here for I bigger than 1 always have positive scalar curvature. So this is the dominating part of the metric on these HIs. So this is what I call distinguished metrics. And by this I mean that at the singularity part, I have a very well-controlled positive scalar curvature property. In the interior, I do not claim anything. And so with this definition, actually, what took me some time to write down, so it was a little, was not so easy to find that. Here we have a very fundamental fact that you know from usual manifolds, closed manifolds or manifolds with boundary, namely the space of distinguished metrics on such a P-manifold is non-empty and contractible. You can work with these metrics such in the same way as with usual Riemannian metrics. The only thing is that at the singularity part, we have these additional conditions involving the matrix HI. And now I have a slightly confusing picture how that is done. But in principle, it is this a process here, and I can stress one important property of positive scalar curvature geometry which comes in here. Namely, so what is easy is to construct these metrics G omega on these parts A omega, for example, GI, GIJ, GIJ, and so on, such that we have all these compatibility conditions. But the problem is that then the condition that on the boundary, like here, we have the metric HI appearing with positive scalar curvature and dominating the whole thing. This additional property, this needs additional work. And what I can do, I can start with a metric on my manifold like this. I take a very large lambda to make the scalar curvature small this piece, and then I use the color regions to connect these with the standard metrics on these HI pieces. And this means that along this boundary here, along the singularity, we always have positive scalar curvature metrics because we always see one metric HI without any lambda, right? And that this is possible uses two basic facts in positive scalar curvature geometry. The first is that if you take the product of two manifolds, then the scalar curvature is the sum of the scalar curvature. So if you have HI and here you take a very large lambda, then this thing has positive scalar curvature, this thing has positive scalar curvature, and so on. And the next thing is that if we move from here to here and from here to here, so we have an isotopy of positive scalar curvature metrics, then we can construct a concordance of positive scalar curvature metrics by just making this collar wide enough. So we move along these collar coordinates very slowly. So this is a rough picture how we prove this fact, and this shows that the notion of distinguished metrics in this sense is probably the correct one on manifolds with Bars-Sullivan singularities. And now we have an important connection to homology. Namely, we can in fact take these singularity types, P1, P2, and so on, in such a way that they generate the oriented Bordism modulo torsion. So this is, these are classical computations of Milnor and Novikov, and a polynomial ring in generators of degree 4i, and we can take these manifolds as generators. And this is actually the one of the most important theorems of the theory here proven by Bars in his paper, that these manifolds actually give a full description of the homology of a classifying space of a group gamma, B gamma, if that group is of odd order. I could have stated this theorem slightly differently, namely that Bordism with manifolds with Bars-Sullivan singularities away from the prime 2 is isomorphic to homology theory. But I think this is a more concise way to state it. And now we have a very nice thing. On the right-hand side, we have a group which can be computed efficiently with kind of elementary algebraic topological methods. On the left-hand side, we have an object, Bordism, of geometric objects that possibly kind of allow a discussion of positive scalar curvature geometry. So this is a very important statement here in this context. So, okay, so to phrase it again, homological cycles are modeled oriented by these P manifolds. Okay, so once we have that, we can write down another construction machine, namely positive homology. What is that? Okay, so we just copy the definition we had before, but we have to remark that in this choice that I made, Pi as generators of the Bordism ring, we can actually take these generators also with positive scalar curvature metrics. Actually, this is the main observation in the paper of Lawson, Gromov and Lawson, when they proved existence of positive scalar curvature on non-spin manifolds. Okay, so this means we have a notion of distinguished metrics and also of distinguished metrics of positive scalar curvature. So remember, distinguished metrics means along the singularity part we have a certain restriction, and positive scalar curvature means positive scalar curvature everywhere. Okay, so then we just take the subgroup here, represented by Bordism classes. Now we take P manifolds, and the condition is that these admit distinguished metrics of positive scalar curvature. So this is now our definition of positive homology. And the point is here that, so this also involves classes that cannot be represented by smooth manifolds. So it's a more flexible notion of positiveness, namely directly connected to homology theory of these odd order group gamma. And here we also have a Bordism principle, which now becomes a homology principle. A version of that was proven in doctoral thesis of Sven Führing a couple of years ago in a slightly different context, but I put it here because important ideas appeared there, and then I proved it in this context again. So the point is here that if you have, so the idea is the following: you have a manifold with Bar-Sullivan singularities. You have these manifolds. We have these corner regions, but along the boundary, you have a positive scalar curvature. This is this distinguished property. And this means that you can basically pass to a smoothening of this manifold with corners and still have positive scalar curvature. So then you can connect the whole picture to the smooth world, which is already understood. So this is the reason why it's good to work with distinguished metrics of positive scalar curvature, such that we have good control along the singularity region. Okay, so we can now see when such a smooth manifold emits a positive scalar curvature metric, the classifying map must map the fundamental class to the positive part. So this means we have to compute the positive homology. For example, of this group. This is an abelian P group of rank R. It's not elementary abelian because K1, K2, and so on can be bigger than 1. And for these groups, we do not have a Bordism calculation. But we do have a homology calculation, and this is done inductively. So if we just have one factor, then the homology of the classifying space, maybe you've seen that in some lecture course or seminar, is the following. In degree D, we have in odd degrees a copy of Z mod P to the K, and in even degrees, we have 0. That's the computation of this homology of the classifying space of Z mod P to the K. And it's also important to see that we have geometric generators of these groups here, namely length spaces that we saw before, right? So these length spaces represent these homology classes. And so we know that in dimension bigger than 1, we have positive scalar curvature metrics. So the positive part of that homology group is nothing but the homology in degree bigger than 1. This is easy. How do we pass to higher ranks? Yeah, we write down the Künneth exact sequence. That is the tool of our choice in order to calculate the homology of B gamma prime, which is a product of these two groups. On the left, we have a tensor product of the homologies. On the right-hand side, we have a torsion product. And in the middle, we have our homology. So you derive these sequences in algebraic topology courses. And it is already one of the non-trivial tools because it is a little difficult to understand what this thing here really means. The left-hand side is easy because this map is just represented by taking Cartesian products of P manifolds. So remember, elements here and here are represented by these P manifolds together with maps to these spaces, and then we just take Cartesian products. This is easy. But the pre-image of beta, so if we want to understand which elements map to these elements here, so these involve a Toda bracket construction. And I think this appears in other parts of geometry and topology again and again. So let me quickly recall what this means. So this is, the point is that if you have elements in these groups of the same order, P to the K, then there are two different reasons why the product of these elements is 0 homologous. Namely, so we take these two groups, gamma I. You take two classes, and both have order P to the K. Because we are basically working in Bordism theory, we can take the disjoint union of these manifolds AI, p to the k-fold disjoint union, and these bound. So these are zero bourdoned, and so we find bounding maps, Fi, and then we can write down the Toda bracket. This is what I said. There are two reasons why the product is a boundary. Namely, we can pass to W1 cross A2. This is the first way to look at it, and the second way is taking A1 cross W2. W1, W2 are the co-bounding manifolds. And so now observe that the boundary of both these pieces is equal to p to the k times A1 times A2. So these two can be glued together. And we get an interesting map here. So we have a certain indeterminacy lying in this subgroup. But one property is important, namely if these two classes are positive scalar curvature, then also this Toda bracket is positive. Why is that? Okay, so this means by definition A2 and A1 carry positive scalar curvature metrics in the sense of distinguished metrics, and then we can do the same trick. We multiply them with, in this case, with a small constant to make the scalar curvature very big so that it dominates the scalar curvature of W1. So, I mean, W1 is a manifold that we don't know, so we don't know if there is positive scalar curvature or not. But we know that this whole product, this Toda bracket, carries a positive scalar curvature metric if both these classes are positive. Okay, just to make a short remark here, because this was asked at another occasion when I gave this talk. People who know Bars-Sullivan singularities, manifolds with them, know that there is an annoying fact or a difficult point in the theory, and this concerns products of manifolds with Bars-Sullivan singularities. And let me point out this technical issue, which is quite important. The point is, if you have two manifolds with Bars-Sullivan singularities, A and B, we look at the ith boundary component. This is AI cross PI, BI cross PI. And now we would like to define the ith boundary component of A cross B, which is, of course, the union of these two parts. And now let's look at the intersection of these two, where these two are glued. We see the product of the two boundary parts, and this is AI cross BI cross PI cross PI, two copies of PI. And the problem is, if we want to write that thing here as a manifold cross PI, one manifold cross PI, then we do not know what PI is the correct one. Because both these, they switch their roles. So the first one comes from this part and the second one comes from this part. And then it's unclear which one is really the singularity PI. So then, therefore, one has to apply another construction which takes care of that issue. One has to glue in a new handle that allows one to switch these two factors. And I've drawn this picture because in the literature, this point is usually explained, at least to my taste, in a very confusing way. It goes on for pages and pages. And then it says, okay, there are some obstructions at the prime 2, and away from the prime 2 there is no problem. But of course, in our world, when we do geometry, we need concrete pictures and concrete realization. And this is given by this picture. So on the left, this piece here, the black piece, is one copy of A cross B, and this is the boundary part. Here, the two roles of PI cross PI have to switch, here again, and after passing to 2 times this product, we can actually solve the problem by gluing in a handle where we can, which can be used to switch the two factors PI cross PI. And in our positive scalar curvature world, this is not a problem because this thing here, I mean, it's a hexagonal piece. And if we want to look at metrics which are of product form near the boundary, there are no ones with positive scalar curvature. It would contradict the Gauss-Bonnet theorem. But we can again make, by a scaling argument, this negative scalar curvature contribution small compared to the contribution that comes from these PI pieces. So this admissible product issue, this can be resolved. It's quite important because otherwise we cannot pass to products of manifolds and discuss positive scalar curvature in the world of Barr-Sullivan manifolds. Okay, so now with this knowledge we can look at the induction step. And as we said, here we take products of P manifolds, and if one of the factors is positive, then the product is positive. This is what we like, and so here we can then easily imply induction. But here we have a problem, namely here we just have positive scalar curvature if both factors are positive. And this is not the case if one factor has degree 1. Right, and these Toda brackets have to, so they appear actually even for non-toral manifolds. So here we have a problem. So this is how far we get at this point. So we can show positivity for most classes, so to speak, but there is one particular problem, namely Toda brackets with one-dimensional classes. And this actually took me quite a while to resolve that issue, because the only way I see to do that is that we must find a way to restrict to a certain subgroup of this group. So I have to deal, or I want to deal with just specific toral classes in this group. I cannot deal with all classes. I have to exclude some, and I have to find a way to discuss a certain subgroup here which I can treat with that method. And this is actually possible using homological techniques and techniques from stable homotopy theory. Namely, I introduce a new homology theory. It's derived from Brown-Peterson theory. So recall that's homology theory, a generalized homology theory like K-theory or Bordism. For each prime P with these coefficients, it's a polynomial ring. And the point is that the unitary Bordism spectrum splits as a sum of suspensions of these Brown-Peterson spectra. So these are actually a way of thinking of it is that they are a sort of skeleton of Bordism theory. What I do, I simplify the theory so that it gets approachable by passing to a linearized version. I divide out the square of the ideal generated by these generators V1 and V2. And the point is that this new theory sits between the Bordism theory that we cannot compute, it's too difficult, and the homology theory which we can compute, but that we cannot explore completely in terms of positive scalar curvature geometry, because we have the problem with the one-dimensional Toda brackets. And this theory, which is pretty close to that one, this can be analyzed to such an extent that I can prove that for an abelian P group, gamma, and P odd, I can actually show that all toral classes here that lie in the image of that map, right? So this is, of course, a certain restriction. So these can be treated by an inductive argument, as I've shown before. And I mean, these Toda brackets with one-dimensional classes still appear, but then they can be discussed in a different way, because we always have the freedom to apply group homomorphisms to our group gamma prime and try to cover these classes in a different way. But for this, I need to pass to this new homology theory. And the computation here that goes into that theorem here is rather difficult. So I have to prove a Corner-Floyd conjecture for this intermediate theory, and then to really do concrete calculations with the Atiyah-Hirzebruch spectral sequence for that theory to make sure that all classes that lie in this image can actually be treated by this inductive argument that I presented here before. Okay, so in this way we can deal with the elementary with the abelian P groups. Unfortunately, I'm not able to say anything about spin manifolds in this context. It's just about oriented manifolds, which are not spin. And for the spin case, I would have to deal with KO homology, and I have to find a correct analog of this theory here. And so far, I haven't been able to do that. So this is still work to do, but at least for the non-spin case, we have a fairly complete answer for abelian fundamental groups of odd order. And hopefully, this sort of more general notion of positive scalar curvature metrics can also help us to deal with other fundamental groups, but I do not have any concrete results in that direction so far. So thank you for your patience.
Other questions? Go ahead.
Yeah.
But what excludes that? Because every spin manifold is orientable.
Yeah, that is true. But so if I write down the homology principle for spin manifolds, actually I glossed that over. Here, let's positive homology. So if you have spin manifolds, then you have to work with positive K homology. You are not allowed to compute these groups anymore. You have to deal with these more complicated groups, and unfortunately they are really considerably more complicated to calculate than usual homology. Yeah.
More questions? So imagine that you would be allowed to change the positive scalar problem into a slightly different problem, Riemannian geometric problem that would fit better with your techniques. So,
okay, do you have a problem in mind?
No, but
of course, yeah, that is of course
so
a very yeah. So I mean, what is the game like? We have different tools or toolboxes, right? I have the geometric toolbox. I have the homological toolbox, topological toolbox. And what I did here is to I try to refine the geometric toolbox in a way such that my computations on the topological side give better answers, right? And of course, it's not clear to me, so where is the ideal balance? And as you say, maybe that is not the correct problem to look at, because especially with these one-dimensional classes, this is something that appears in positive scalar curvature geometry. But if we looked at non-negative scalar curvature, right, then this problem does not appear. We can deal with this case right away. I did not mention that because this theorem was already mentioned in the paper by Botvinnik and Rosenberg, or by different methods. So they prove that if you have a manifold with abelian fundamental group of odd order, it has non-negative scalar curvature metric. So
and this is very close from the positive scalar curvature problem, right? A manifold that admits non-negative scalar curvature, but not strictly positive scalar curvature.
Like tori, for example.
Yes, then they admit Ricci flat matrix, right? There is a...
Yes, of course, you can go on with the discussion in this direction.
Yes.
And I admit there is still room to play around and to find the correct setting so that that these methods maybe fit together more nicely than in the positive scalar curvature context.
There are more questions. If not, let's thank Bernhard again.